There we go. So what we'll do today is to take a look at practice exam questions because the exam number 2 for this class is next Monday. Okay, so we have 1 week from today for the second exam. So the second exam will focus on material that is introduced after the first exam, after the end of the first exam, but it also includes the floating point number topics, because that was not included in the first exam, so now it's in the second exam. Is that okay? So everything from the second exam, from the end of the first exam, including floating point number representation, all the way to instructions that we have talked about up to now, up to today, not excluding the lab tonight, okay? That is excluded. But everything that we talked about up to this point is included in the scope of the second exam. So it's quite a bit of material. So I can show you some of the exams that I have used in the past. And the best way to do it is to share it into the folder. I think some are shared already. So let me double check and see how many exams are already shared in the shared folder. So when you go to the shared folder, there's a folder called Old Exam 2s. So there are a few exams over here. These are fall 17 exams, so they are most recent, so they should be relevant. How many of you have kind of taken a look already, even without me prompting? Not yet? That's okay. We can take a look now. So we'll take a look at these. The scope may not be the same because sometimes I change the order or how much time I spend on each topic. So it is possible that we may not be using the same topic. And this one doesn't seem like it has got floating point numbers. So let me open up another one that has floating point numbers first, because I think that is kind of important. So we look at old exam 1s, and we can look into the one from the last semester, because I'm pretty sure this one has floating point number questions. Okay, keep going. I think if I remember correctly, it's the last 2 questions that are floating point number related. There we go. Okay. All right, so question number 5, which is this one here, is asking, okay, let me center the whole thing first. So this question is asking, how do we represent the value of negative 5.625 as a double? Now, when I say double, it is just an abbreviation of double IEEE double precision floating point number format. Okay, I just don't want to have to write the entire thing. So every time I say double, in this context, it's the double precision floating point number representation. Specify the bit pattern in hexadecimal. So I'm telling you guys, how to write out the bits. So don't give me 64 bits, okay? Because I cannot read 64 bits, even though in this case, most of the bits are all zeros, okay? Only a few bits are not zeros. And show your steps, including how you figure out the various parts of a base 2 scientific notation and how the parts fit together in a double. So what are the 3 parts of a double precision floating point number? The mantissa is one, or the fractional part of the mantissa. What is the another part? The sign bit. Very good. And the third part? No. Which part controls the magnitude? The mantissa controls how many. The sign obviously just controls which direction of the number line. So which part controls the magnitude? The exponent, okay? So those are the 3 components, and you have to show me how you figure out those individual components for this particular number, okay? All right. So what I'm going to do is to use my tablet here, so I can just kind of hand draw the whole thing for you guys. And you can use diagrams too, okay? As long as it is clear, how everything fit together. You can also use diagrams when you explain your answers. And I left my stylus at the hotel too. So this turned out to be somewhat of an expensive trip to Southern California. So I got a new stylus. And this time, it's tethered. The only danger of doing this tethering is my cats really like it too. They like to chew on the wire, the string, and go like, come on, let me play. Hmm? There's some stuff you can spray on. It's based on apple seeds, and it's supposedly exceedingly bitter. I tried it, and it is quite bitter. But it won't work if my cat starts to have a taste for that sort of thing, which I won't be surprised. Okay, so let's see here. That is not for you guys. And school 310, Monday, Wednesday. Cool. All right. So we want to figure out the 3 parts. Okay, so we want to figure out what parts again. We have the sign, which is the easiest part to figure out. Oh, you guys cannot see a single thing because I haven't started the advisor application. Yep.
Are you recording?
I believe so. I'll check that as soon as possible. Okay, so let me check the recording first. Yep, we are recording and there is voice. Okay. It should be activated already. Yep. Okay. Try that one more time. Okay, so it may not be this one. This one wants me to pay for the app again. Did I try the first one or the second one? Try that one more time. There we go. Uh-oh. All right. Maybe not today. Stop teaching for 1 week and everything falls apart. And I'm not even teaching Android programming. If you teach Android programming, you stop using Android Studio for like 2 days, there'll be tons of updates. Yep. It's like your Android installation is so outdated now that nothing works. Okay, well that's okay. I can explain this one without using my tablet. It's just going to be a little bit more boring. That's okay. All right, so I'm just going to type it here. The sign is going to be a what? The sign as one single bit is going to be a 0 or 1. It's going to be a 1 because the value is negative. And let me just repeat what the number is. The number or the value that we want to represent is 5.625. Let me just double check. Yep, negative 5.625. Okay, so that's the sign. That's the easy part. So next we need to figure out the exponent as well as the mantissa. So it's difficult to only single out one of them, although there is a way to do it. If you want to single out just one of them, you look at this number and then you ask yourselves if you can only use a magnitude, like a multiple of something, what is the largest unit that you can use that can represent this value exactly? In other words, what exponent of 2 should you use as the unit so that you can just say, oh, there are so many of these powers of 2. Okay, sorry? 2 squared? No, I was more thinking about 2 to the power of negative 3. 0.125? Yep. Because if you look at this number as number of 0.125s, you can specify the same value as a quantity times 0.125. Is that making any sense? Okay. So you can use it. You can use this method. So you look at this number, negative 5.625, and you divide it by 0.125, which is also known as 2 to the power of negative 3. So that should end up as an integer. The sign part is not important now because we took care of the sign using the sign bit. So we can ignore the sign at least at this point. For each one, there are 8.125s. So the 5 accounts for 8 times 5, which is 40 already. Is that okay? And then 0.625 itself is 5 times 0.125. So we have 85 of 0.125s. Is that okay? So let me just write it down first. It doesn't seem to make sense. 45. Sorry. Yep, not 85, 45. Because I was just going through some mental math and go like, no, that doesn't make sense. Okay, so there are 45 of these. In other words, the value that we want to represent is negative 1, which is taken care of by the sign, times 45 times 2 to the power of negative 3. Is that okay? Is everybody convinced that we can rewrite negative 5.625 as a base 10 number as negative 1 times 45 times 2 to the power of negative 3? Okay, so once we get here, then what else are we supposed to do once we get here? We cannot use 45 as a mantissa because the mantissa is supposed to be 1, it is supposed to be normalized, and then what is represented in a double precision floating point number is just the fractional part. It's excluding the 1 point, okay? So we have to somehow adjust this number so that it looks like that. Okay, so the next step we need to do is to look at 45 and say, okay, what does 45 look like as a base 2 number? Convert it to base 2. Now, I'm not going to give you guys something that is really hard to convert that you cannot do it by hand. 45, we can do it by hand, okay? Because we can look at this and go like, I know there's a 32. After a 32, we got an 8. After the 8, we got a 4. After the 4, we got a 1. Okay, so just by using mental math, I can break it up into a sum of powers of 2 already. You can use a calculator, a scientific calculator. You can use it during the exam. So you might want to try out how to use a scientific calculator to do this. So once I know 45 is the sum of these powers of 2, then I can say it is 1 followed by 5 zeros in base 2, plus 1 followed by 3 zeros in base 2, plus 1 followed by 2 zeros in base 2, plus 1 followed by 0 zeros in base 2. In other words, the number of zeros is reflecting the power, what is 2 raised to which power. When it is 2 raised to the power of 5, it is 1 followed by 5 zeros in base 2. When it is 2 to the power of 3, it is 1 followed by 3 zeros in base 2. Does that make sense to you? It makes sense in base 10 too, right? Because what is 1,000? 1,000 is 10 to the power of 3. And that's why it's 1 followed by 3 zeros in base 10. So when you draw the parallel between base 2 and base 10 like that, base 2 is not really that much different from base 10. So when you add all of these numbers together, then you end up with 1, 0, 1, and then 1, 0, 1 in base 2. Can we buy that? Okay, cool. All right, so this is our mantissa at this point. But this mantissa is not normalized. Okay, because normalize means I want this to look like 1 point blah 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 blah. Okay. All right. So I'm just doing it really step by step. 1.1 excuse me 101 101 with an implicit point here. Okay, times 2 to the power of -3, and we want to re-express it until the mantissa looks like the format that we want it. Okay. Can I move the binary point just one at a time? Okay, I know this is going to be a little bit boring to some of you, but I think it is a good exercise. So if I shift this binary point from here to here, what do I need to do to the exponent of 2 that is specifying the magnitude? Decrease or increase? Increase by 1. Very good. Yep, exactly. Because what we are doing here is we are dividing the mantissa by 2, and as a result we have to multiply the 2 somewhere, and we can adjust the exponent to get that part done. All right, so the next step is to look at this mantissa, and then we go, that's not normalized either. So we have to shift the binary point from here to here, and as a result we have to add 1 to the exponent of 2 again. So now it is 2 raised to the power of -1. And then we look at this one more time and go like, okay, so we can. So I'm just doing it really step by step. Okay, you can see where this is heading. And then we can look at this 1.1101, 10.1101 in base 2 times 2 to the power of 1. And this is our last step here. It's 1.01101 in base 2 times 2 to the power of 2. All right. So you can do a sanity check, okay? Does it make sense? The magnitude of the number, if you just ignore everything to the right-hand side of the decimal point, we got 1 times 4. That's pretty close to 5.625, okay? Because this will take care of everything from 4 all the way to 7 point blah blah blah. Okay, because 8 is the first time that we have to roll over the exponent. So it seems to make sense. Okay, so now we have this part here, and now we can say, okay, what is the exponent? The exponent that we need to represent is not just the 2, okay, because it is biased. So even though there's a 2 right here, the exponent that we actually need to represent is biased by how much? Do you guys remember? No. It's 1023. It's biased by 1023. So you have to add 1023 to this thing, and you end up with 1000, not 10,000. 1025 is the base 10 representation of the binary bit pattern that has to specify the exponent. So when you look at this number, or when you look at this value, 1025, what does it look like in binary? That's because we have to convert everything into binary. This one is easy because it is 10,024 plus 1. I mean 1024, I keep saying 10,000, but it's 1024 plus 1. And why is 1024 kind of special? It's a power of 2. It's a power of 2. Which power of 2 are we talking about? 2 to the power of 10. Very good. Okay. So that means this is the same thing as 1 followed by 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Plus 1. Okay. Let me emphasize this is all in base 2. So that turns out to be just 1 followed by 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the 1 in base 2. That is what we need to put into the double precision floating point number. It is not the 2 that we really want, the value that we want. It has to be 2 plus 1023 because it is biased by 1023. Don't ask me why it's 1023 and not 1024. That's just how they chose the bias. So are we doing okay so far? Okay. So what is left is the fractional part of the mantissa. So that part is really kind of easy because we are just ignoring the 1 point, and then we just copy and paste the fractional part of the normalized mantissa. So we just paste it here, and then we just say a whole bunch of zeros here. How many digits do we need for the fractional part of the mantissa in a double precision floating point number? There's 1 bit for the sign, 11 bits for the exponent. So that leaves us how many bits for the fractional part of the mantissa? 64 minus 1 minus 11 is 52. So there are 52 binary digits in here. The most significant part is the only part that we care, because everything else are all zeros. So now you put the whole thing together. You put the whole thing together, which is basically the sign first, and then the exponent, and then you have the fractional part of the mantissa. So the sign is a 1. The exponent is 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 zeros, and then another 1. And then the mantissa, or the fractional part of the mantissa, is 0, 1, 1, 0, 1, and then followed by the whole bunch of zeros. So we just have a whole bunch of zeros after that. Okay, if you get to this part, you get most of the credit for this particular question, but not every single point possible, because the question did ask specifically to specify your bit pattern in hexadecimal. So there's one little last step that you have to do. So that one little last step that you have to do involves chopping things into blocks of 4. So you have to look at these 4 as 1 block, these 4 as 1 block. Okay, that's 1 block already. That's 1 block. Hey, we got a 1 0 here. That's not a block by itself. Give it 2 more zeros as 1 block, and then all the rest are blocks of zeros already, so they're not particularly interesting. Is that okay? You know how we chop it into blocks of 4 from the left. Okay, the most important part is you should do it from the left-hand side. So once we have this, then we can look at 1, 1, 0, 0. Basically, we look at these 4 bits. Even though 1 is from the sign and the other 3 are from the exponent, it doesn't matter. Okay, just kind of group them together, and then you ask what hexadecimal digit is corresponding to 1, 1, 0, 0 in binary. That turns out to be C. Okay, so here's a C, and then you look at these 4 zeros. Okay, that's an easy one. That's just a 0. You look at these 0, 0, 0, 1 is just 1. And then we have 0, 1, 1, 0, which is a 6. And then we have 1, 0, 0, 0, which is an 8. And then followed by a whole bunch of zeros. So how many zeros do we need to pad this whole thing? 1 hexadecimal digit specifies 4 bits. And we know this entire thing is 64-bit wide. So how many hexadecimal digits do we need altogether? 64 divided by 4 is 16, very good. Okay, so we need 16 digits. This is taking care of 5. The rest are all zeros. So you just need to pad the whole thing with 11 zeros as a hexadecimal number. So we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that would be the answer. But you need to show me the steps, just like what how the way I worked on this on the projector. Are we doing okay so far with this one? So the question that I'm going to ask you, will not be very difficult to convert. In other words, I'm not going to give you like 2.3 to convert it into a double precision floating point number. And you might be thinking, 2.3, how hard can that be? It looks so simple in base 10. Well, just because it is simple in base 10 doesn't mean it's going to be easy in base 2. It's going to have recurring bit patterns. Okay? Now, it's not like we cannot do it. It's just take a lot of time to figure out the repeating pattern, and then you have to do all the hexadecimal conversion because of that too. So I'm not going to give you something nasty like that. I might give you, I don't know, like larger values. 768. And people think 768, that's pretty difficult to convert because it's a big number. But then you have to think about, can you re-express 768, 768 as a multiple of some powers of 2. So you think about, oh, we can use 2 to the power of 0. There are 768 of those things. That's not helpful, right? So you have to find the largest power of 2 that is a factor of 768. We know it cannot be 512 because 512 is too big. What is one step smaller than 512? 256. So what happens when you divide 768 by 256? You can use a calculator during the test, but I was hoping that you guys do not need to use a calculator. There are 3 of them, exactly. There are 3 of them. Okay, because 3 times 250 is 750 already. And then what is left is 3 times 6, which is 18. You add 18 to 750, then you have 768. Okay, so there are 3 of them. That means the quantity is just 3. But your original exponent is going to be 8 because 256 is 2 to the power of 8. It turns out to be easier than this one. How do you represent 3 as a binary number? Does it take a lot of time to convert that one? 1, 1. How do you normalize 1, 1? You only have to shift it once. So 768 seems to be difficult compared to this one. As it turns out, it is much easier. Now, if I give you 768.5, that gets a little bit more difficult. So you might want to do these things, okay? So you might want to give yourself examples of, numbers to convert, okay? Start with 768.5. And then you try to figure out why that is a little bit more tricky and more time consuming compared to 768. So until you do it by hand, you won't actually get the feel of it. You might be able to think of it and go like, oh yeah, we have a whole bunch of zeros between the 2 ones, okay? But how many zeros are between the ones, okay? You can only figure it out when you actually work on it. So are there any questions about this one? Question? How many zeros are here? Well, altogether we need 16 digits. So we have 5 digits as the most significant portion. So how many zeros do you think we need? Sorry? 11, that's right. Well, that should be 11. I'm not sure whether I actually do have 11 or not. Yep, I think there are 11. So the other trick you can do, to make sure that you count correctly, is to block the hexadecimal digits also in blocks of 4. So this way it shows really well whether you have the right number of digits or not. It's kind of the same thing that we put a comma between every 3 digits in base 10, except in base 2, okay, it makes more sense to chop it in blocks of 4. Question?
You said you did I think you figured out the exponent a different way, just like dividing by 0.125. What would be the other way of figuring out, I guess?
Oh, the other way? Oh, the other way is to look at it, is to do the actual conversion. So you look at 768, and then you do the brute force way to convert it into a binary number. So you can do it that way too, but it turns out to be 1, 1, and then 1, 2, 3, 4, 5, 6, 7, 8. So you can do it this way as well. So it all depends on which way is more intuitive to you. You can do it this way if you want to. You can also do it the opposite way, which is to look at 768 as 3 times 256, and then you say this is the same thing as 1, 1 in base 2 times 2 to the power of 8, and then start with that. So you can work with either one. In the top one, if you start with 1 1 followed by 8 zeros in base 2, then you just have to shift 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. Okay? But your exponent, your implicit exponent is 0 to begin with. If you do it the bottom way, then you only have to shift it once, but you do have to figure out that you start with an exponent of 8 instead of 0. So it all depends on which way makes more sense to you or more intuitive, but you can use either method. So do we have any questions about the conversion process? No questions? I know this is eons ago. And by the way, what is an eon? Yes, but I think there's a specific number to it. Okay, now I need to know. Because I asked the question, so I have to know the answer. What is an Okay. A unit of time equal to 1 billion years. Yep.
I don't think I was alive a billion years ago.
Sorry?
I don't think I was alive a billion years ago.
You were, but just in subatomic particles of some kind, probably as hydrogen, atoms, somewhere in a prototype star.
I don't define myself as a series of atoms. I define myself as a what is it called? Pattern. As a collection.
That is self-conscious.
True.
So from that perspective, no, you have not existed yet 1 billion years ago. But all the stuff that you're made out of already existed, just in pieces all over the universe.
Remember, when you die, your atoms are not going to notice a single difference.
But in order to make you, a lot of stars have to die.
It's true.
That's how we got iron.
I'm made of stardust, but so is trash, so it doesn't really matter.
Actually, technically, we are made out of star poop, not star dust, because iron is actually the waste product of fusion.
Or star explosions in the case of everything higher than iron.
Oh yeah, absolutely.
Star dead stuff.
Yep.
Exponent always 11 bits, or is that just
Is the
exponent always 11 bits?
yes. In a double precision floating point number, the exponent is always 11-bit wide. All right. So when you study and you go, okay, I need a more definitive source to tell me what a double precision floating point number is. So you look up IEEE, just double, okay? And Google automatically figures out, oh, you want the precision, double precision format. But if you just look this up, the first entry is Wikipedia. And Wikipedia gives you a pretty graphical way of representing the whole thing. The light blue one is the sign, which is 1 single bit. It's the most significant bit. And they even give you the bit numbers, okay? The green part is the exponent. There are 11 of those. And then the pink part is the fractional part of the mantissa, and there are 52 of those. So if you just look it up, they will give, you can find plenty of references of, what it looks like and how to do the conversion. The bottom line is, do we understand what each bit is contributing to the value that is being represented? That is the bottom line. Because once you understand how each bit out of these 64 is influencing the value being represented, then you can come up with your own way of doing the conversion. Whatever way makes more sense to you that you can show step by step is going to work. Is that okay? Are there any questions about the representation itself? Now, Wikipedia gives you 2 equations to tell you what value it is representing. There's a top one and there's the bottom one. So that is also something that you can look into. And once you understand what it means, then the rest just kind of follows. You can also go back to the labs that we did with floating point number conversion, because those particular labs were designed to help you understand the whole idea of how do we do the conversion. We didn't do all the do all the shifting so that we normalize the mantissa, but we did everything just short of normalizing the mantissa. So are we doing okay so far with this? So cool? All right. So we look at the test question. The second last question is also floating point number related, and I think it's the opposite direction, or maybe not this one. Okay, let me just kind of scan and find out whether it is in here or not. Nope, it's not in here, so it has got to be one of the other ones. Okay, well, I'm just checking the one before this one, and it's probably one of the last few questions. Maybe not. No. Okay. Now that's a question one. That's a first exam. So I'm just going to give you an idea of what other type of questions I can give you. I can give you the hexadecimal representation and then ask you what value it is representing when we look at it as a double precision floating point number. In other words, I can reverse the problem that we're solving. So I can give you this particular hexadecimal number as a starting point, and then reverse the question and ask you what value is it representing as the bit pattern of a double precision floating point number. So you basically then have to chop it up first, right? So you have to chop it up and say, okay, where's my sign bit? Okay, where's my exponent bits? 11 of those. Where are my fractional mantissa bits? 52 of those. And then you look at those specific parts, okay, and then you do the calculation and figure out what value it is representing. So that's basically just kind of the same thing, except it is reversed. I give you the bit pattern, you tell me what value it is representing. The original question is giving you the value, and you have to tell me what representation what does it look like as a double precision floating point number. So are we doing okay or not? More or less. Okay. We have one more class before the exam, so when you're studying or when you try out some of the examples and you go like, I'm not sure how we do this one, bring it to class. We will talk about it. Okay? All right, so I'm going to assume that this part is done, okay? And then we can move on to other parts of the questions. If you do have questions, about this one, go ahead and ask me. Okay. Oh, okay, I skipped this one. We have exactly the same kind of question. I give you the bit pattern representation, and I ask you what the value is. Do you guys want to work on this one? No? Okay. Okay, let's check out some of the other questions. This one, I'm not going to ask this one. I think this is still exam one, so the rest of this exam one does not apply anymore. So we'll skip to the exam 2 questions. Unfortunately, I have not gone over enough material about C programming. So, question number 5, like this one, is not going to be in your exam. So I'm not going to give you the assembly code of a subroutine and then ask you to reverse engineer that back into C code. Okay, so but you can expect this to be in the final exam, but not in exam 2. So we'll skip this one because we have not gone through enough material for this. Now, the fourth question, on the other hand, is something that I can potentially ask you. So it is asking you about, I'm adding a new opcode that specifies, the following, patterns, okay? So I give you the names of the signal, and I give you the zeros and ones for the different slices. And the question is asking, what does it do? Okay? So how do you answer a question like that? I give you the microcode slices already dissected into the names of the tunnels and whatnot. So what else do you need to answer this question? Luck is not one of those. Luck has nothing to do with this. What are you going to bring to the exam? It's open book, open notes. The diagram, the schematic of the processor. Okay, so you definitely want to bring schematics, not only of the processor, but also of the register bank and also the ALU, just in case you need those. Okay, all right. So let's go ahead and start up LogicSim so that we can look at the schematic of the processor. There's one already in the share folder as well. If you go to, I cannot remember where I put it. I'm going to assume it's processor. It's going to be a PDF document. Yep, there we go. All right, so I got the PDF already done for you. All you have to do is to find the printer and print it out. If one is not enough, print out like 5, 6, whatever, double-sided, okay? So now the question is, when you look at this, okay, how do you answer the question? Assuming you have access to a piece of paper that has the schematic on it. So then what do you do to answer that question? Yep. So you basically, if you're short on time, okay, you put your focus on the things that turn on and turn off stuff. All the ENs are important. All the multiplexers, MUX, they're also important. So in this case, let's look at the first slides and see what it does, okay? Microcode pointer select being a 1 simply means that we're incrementing the microcode pointer so that we get to the next one. So that part itself is not really too useful to answer this question. PCEN being a 1 is kind of important. Anything that has an EN that is turned into a 1 is important because that tells me that something is enabled, which usually translates to something is about to be updated. Okay, so that's why it's significant. In this case, the program counter is going to be updated in the next rising edge, so it's important. PCMux controls how the program counter is going to be updated. Just by looking at this, I cannot tell you how it's going to be updated. So you have to refer to the diagram to find out how PCMux is going to affect the processor circuitry so that you can figure out how it's going to be changed. So let's switch back to the PDF and try to figure that out. And where did I put that? I think it's still here. There we go. All right, so this becomes kind of difficult for this class, when I'm using a projector like this, because I have to pan and control the whole thing. Okay, so we can see this is PCMux, and PCMux, as the name implies, goes into a multiplexer, okay, like this one. When PCMux is a 7, what am I connecting from what is the input that I'm connecting to the output? Which input am I connecting when PCMux is a 7? The inputs are labeled 0 up to 7. So when the selection is 7, which input am I using to connect to the output? The 7th one, input 7, which is a 1, correct, okay. So it's a constant of 1 that is connected to the output. Great, the output is another tunnel. What do? Track it down, okay. So where is PCMux? PCMux goes to a multiplexer that controls how the program counter is going to be updated. Okay, and the program counter is located right here. And then you can say, okay, I know PCMux is a 1. It's a constant. It doesn't depend on the flags or anything like that. It is a constant. PCMux is right here as a tunnel. So when this selection is a 1, I'm selecting input 1 to connect to the program counter. So now I track down input 1 of this multiplexer, and it's coming from another multiplexer. Great, because it's coming in from this particular multiplexer. So now I had to figure out what this one is going to be. We know PCMux is a 1 already, but we don't know what is RO0EN. Okay, So it's going. So now it's time to go back to the question and figure out, okay, what is RO0EN, which stands for Register Output 0 Enable. So you go back to the question, and RO0EN is a 0. So we go back to the diagram again. So this is a 0, but it's negated before it goes into the AND gate. Okay, so that means on one side, PC mux is a 1 already. On the other side, we have RO0EN, which is a 0, but since it's negated, it is also a 1 going into the AND gate. So we have 1 and 1, so the output is going to be a 1. So that means input 1 of this multiplexer is connected to its own output. So now we track down that one, okay? Now that one is a little bit harder to track because it's this wire, and it goes to here, goes down here. It goes to several places, but the more important part is where it goes to the right-hand side. And you can see this one goes all the way around here to the data port of RAM. In other words, I'm using the data that I'm reading from RAM to update the program counter. Is that making any sense? Okay, how I track down how things are connected. Now, how do you do this, with enough speed in the exam? Because it's not a question of whether you can do it or not. It is a question of whether you can do it in time or not. Okay? So here comes the studying part. How do you study? It's just practice, really. I mean, it really is just practice. You practice with, guess what? Instructions that are already implemented. Okay, you take a slice of the ROM, you break it apart into those individual pieces, make a table just like what I did, or you can go into the C code that generates the ROM code, okay, and use that. It's in the same order, okay? So you can use that to help you practice and go like, okay, I know this is the LDI instruction. What pathways are established with the LDI instruction? Go through the same exercise. Because the more you do this, the more familiar you are with where the tunnels are, where's the program counter, where's the RAM, where are the register bank, and so on and so forth. Okay? The test is open book, open notes, but if you do not get familiarized with this picture ahead of time, having the picture in front of you is not going to help in terms of getting the question done in time. Given enough time, yes, you will be able to do it, but you cannot get it done within the time frame that you're going to have in exam 2. So you do have to study in the sense of you have to read the map and use it enough so that you know where to find the signals. Okay. All right, so getting back to this question. So we know the program counter is updated by the output of RAM. So just to confirm, we can go down to RAM select. Okay. So RAM select is a 1, which means we are telling RAM and we say, okay, we are talking to you. Okay, we need you to work. But when you are addressing the RAM, you have to ask 2 questions. Are we reading or are we writing? And which location are we talking about? So those are the questions that you have to ask. Are we reading or are we writing? That's controlled by RAM load. Load is a 1, which means we are reading. Okay, so we are reading, which means RAM is driving the data port. Okay. So the next question is, who is specifying the address to this thing? Who's controlling which address? We are using the location that we are reading from RAM so that whatever content is at that location is updating the program counter. Address, ADDR, mux, okay, is a multiplexer, so it ends with a mux. Okay, so you go back to the picture, we know it's a 0. So when you go back to the picture, now once again, I know where to find it because I've been using it for a long time. Address mux is here. It is going into the select pin of this particular multiplexer, and it is a 0. So that means we have to follow this path that goes into input 0 of the multiplexer. So when you follow this path, it is coming out of the demultiplexer here. So most likely than not, okay, the register output 1 demultiplexer is going to be a 0, because otherwise it doesn't make sense, okay? But we can double check. That in return is coming out of output 1 of the register bank. So one of the registers is responsible to drive the address bus to specify the location that we are reading. The content that we are reading is going into the program counter. Is that okay? Which register are we reading? Which register is specifying the address bus? Okay, so you go into this diagram and you ask, out of these particular tunnels, which one do you think is selecting which register we are using as register output 1 of the register bank? Exactly. So register output 1 select. This is the tunnel that is responsible to tell us which register is driving the address bus. So now you go back to the table and then you try to figure that out. So register output 1 select is a 3. So which register are we talking about? Register D. Okay, so this is how you analyze a table like this to try to figure out what a particular slice is doing. Okay, there's another way to do this. You can also look at the slices of all the known instructions. Have that available to you, because the test is open book, open notes, right? So you can spend some time to prepare a table of all the known implemented instructions and their microcode slices. When you see a question like this, you look into that table that has all the known microcode for all the known instructions, and you ask, which one does it look like the most? And there's one that looks exactly like this one. Is that okay? So we know we are updating the program counter, which means it is kind of a jump instruction, but we are using register D to do it, to specify which location we are reading to update the program counter. Anything else? Are we using the ALU at all? How do we know we are not using the ALU? Because the enable is a 0, okay? Are we using register output 0? Nope, because the enable is a 0. So out of the register bank, only output 1 is being used. Okay, so that is how you analyze this whole thing. And then the answer to the question for slice 0 is this one here. Slice 0 is just doing this. PC equals to dereferencing register D. You can also write it out in words. Okay, D points to the location whose content is used to update the program counter. Okay, I just found that this is a whole lot easier to write. The second slice is, okay, since I scroll a little bit too much, you know the second slice is just incrementing D, which also means if you look up the pattern of increment INC, it will be about the same as this without the question marks. Because I cannot specify a question mark as a bit, but in a picture like this, I use a question mark to say it doesn't really matter what it is. It doesn't change the operation. Do you see why I can use a question mark for PC mux when PCEN is a 0? I'm not updating the program counter anyway. So what you specify as PC mux doesn't have anywhere to go that is actually going to change the operation, because the program counter is not going to be updated. So that's why I have these question marks, because they don't really matter. So are we doing okay so far with how to approach questions like this? Okay, so when you guys go like this, can you be more specific? Sorry? Yeah, studying, and also use Logisim to help you, because when you use the way you use Logisim to help you understand the processor is when you are in the execute cycle. freeze the frame, okay? And then you try to figure out which multiplexer is connecting which input to the output, which demultiplexer is connecting the input to which output, what component is active, what component is inactive. That will help you understand this whole thing as you execute instructions. So you want to execute simple, very simple instructions. Just pick one, okay? Um, JZI, okay? And then you hard code the Z flag to be a 0, see what happens. Hard code the Z flag as a 1, and then see what happens. Okay? So that's question number 4. Are there any questions regarding number 4? No questions? All right. Okay, so let me do one more thing, just one more thing. I think I lost my terminal with a bigger, oh, there we go. So I want to go to cisp310, go to processor, and go to opcodes. This is available to you as well. This is the source code that generate all the microcode slices. When you look up one of these, okay, let's say decrement, okay. These bits are corresponding to, each one is corresponding to one of the tunnels or one of the control lines of the processor. Okay, so which one is which one? You have to look at the second file. So the other file they have to look into, I think, is microcode.c. Okay, we can just do read only. It has to do with, I somehow, exited the editor without properly exiting it. But that's okay. Everything is about Bitcoin now. All the good GPUs are gone because of Bitcoin.
How's there still money that's been hashed for so long?
Well, it gets increasingly difficult to mine, further, Bitcoins.
I know that.
So unless you have a breakthrough in computational hardware that can inexpensively do all the computation, um, I think the return is not there.
Because I know the people that are making lots of money are these massive factories in China and the Philippines, but I don't understand why people are still bothering to try it themselves.
Well, because China is a country.
If someone's from there can afford 3 warehouses full of them.
Yep. Becomes increasingly difficult to make it worthwhile to mine your own Bitcoin. Does it mean that you cannot get a single one? No. Does it mean that it's kind of difficult? You might be spending more money than you're getting back? Yep. Okay, so corresponding, ucode.c to decrement.c, these are the names corresponding to each entry of the instruction specific file. So that means, if you just look at this, okay, you make a spreadsheet, okay, with all of these names as either rows or columns, as a header, and then you copy these values into the cells corresponding to those things. And if you do it for every single instruction, now you have a table, that will show you, how each instruction is implemented. Is that okay? So that's the reason why I'm showing you the source code of the programs that generate the microcode slices, because it's a very quick and easy way to break it down to the components and go like, okay, how is this microcode generated? Because otherwise, the opposite way is to look at the 7-digit hexadecimal number, break it down into individual bits, and then look at the splitters and see which bit is going where in the picture. That is much more difficult than doing this. So this is kind of a shortcut to do it. Yep, question? Nope, okay. Now, because this is open sourced, it also means that you can actually make changes to this thing too. What kind of changes are we talking about? If you go to, okay, let me highlight here. Okay, you can see there are two functions called write slice that actually overwrites certain locations in the ROM. Um, well, it is ROM actually represented as an array in the program. But that's how I utilize the values of slices. So if you want to um, make a make an automated approach to give you that file that gives you all the values for each particular signal and whatnot, change write slice to output to a CSV, okay? And then you can just import the CSV into a spreadsheet, then you have all the values. So that's another way to do this, is to overwrite write slice as a function. But then, of course, you have to kind of read a little bit of. You can probably junk most of this code first, but then you have to kind of figure out how to do the input-output thing. But the bottom line is, um, this is code for you guys to play with. Okay, if you can play with this code and just say, okay, I'm going to change a few subroutines so that I can use make to automatically generate that CSV that I can import into a spreadsheet and make that table automatically. That's good. But it's resources for you. All right. So let's take a look at question number 3. Question number 3 I cannot ask either because we haven't talked about subroutines. So anything that is subroutine related I cannot ask. That's also subroutine related. So the only kind of coding question I can ask is assuming things are done to registers. So assume register A has a value of which you have to find the absolute value, just like in the previous lab. That I can ask. Okay? But I probably won't ask about absolute value or maximum value or minimum value because we have done all of those in class. I might ask about division. A contains the dividend, B contains the divisor. Do the division so that register C is the quotient, and then register A, which was the dividend, will be the remainder. How do you code it? How do you write a program to do it? Keep subtracting. That's the easiest way to do it. Efficiency is not important. Okay, you just have to do it correctly. Go. So let me just write it down, so that you guys can practice. Okay, so assume the following. Okay, register A is my dividend as input. Okay, so this is the input. This is my dividend. Register B is my divisor. The output of this code is going to have register A as my remainder and register C as my quotient. How do you write this code? In assembly. That's probably a good one to, as an exercise. But now that I use it as an exercise, I cannot use it in the actual exam. Is that okay? It's a little bit more involved compared to the absolute value example, but I don't think it's too hard that you cannot do it. Yep, you have to do it in the loop. Okay, I'll even give you the C code. Okay, so the C code looks like this. You have to initialize the quotient with a 0, so C is initialized to 0, and then you say as long as your dividend, which is register A, is greater than or equal to your divisor, which is B, do the following. What do? You subtract B from A, and then you add 1 to C, because C is your quotient. That's your entire program. So other than the conditional branching that may be a little bit tricky, that's easy to do. Which instruction should we use to initialize register C so that it's 0? LDI is 1, and another way is to do a sub CC. Subtracting C from C would also turn it into a 0. Okay. How do we subtract B from A? Sub AB. Okay. How do we add 1 to C? Increment C. So what is left is the unconditional branch to the beginning and conditional branch to get out, but no longer greater than or equal to B. Wait, if I say that if A is no longer greater than or equal to B, what is the other way to say that? When A is less than B, right? How do we check that? We assume all the registers are unsigned. So how do we check that A is less than B? When A is less than B, let's get out. How do we say that? Not the sign flag. So you're right. You chose wisely to cover your face. But you're close. It's not the sign flag. Which flag do we use to indicate unsigned less than? After a subtraction. Huh? Sorry? We did this in the lab, correct. There are only 2 flags that are really useful to indicate less than. One is B, which is known as carry. Okay, the borrow flag is known as a carry flag. The other one is the L flag, which is a combination of the sign and the overflow flag. Those are the only 2 that we really should be using to indicate less than. So now the question is, out of these 2, which one should we use for unsigned comparison? The carry, exactly, because the L flag involves the sign flag, which is a kind of indication that, oh, it might be useful for signed values, but not so much for unsigned values. So the carry flag is the one that can indicate whether a number is less than another number in a unsigned comparison. Okay? So I'm going to leave this up to you guys to implement as an exercise, but I'm assuming that this really should not be too big of a challenge, especially when you have time to do it. But the more you do it, the more you're familiar with the instruction set, and then the quicker you can do it in the exam. That's the bottom line. Okay, any other questions about this kind of question? Nothing? Okay. What about something that looks like this? I need to initialize multiple locations. Okay, so I'll do it like this. Okay, C equals to 0, while C is less than 5. Array bracket C is initialized to, okay, let's make it a little bit more fun. Okay, 5 minus C plus C. Okay, so how do we do something like that? Checking whether C is less than 5 is easy peasy. So now the real question is, how do we figure out which location we should store as ARR array, bracket C. And we assume it's an array of bytes, okay? It's a char array. So how do we do this? So in the assembly program, ARR is going to be a label, and it's going to have 5 byte thing after that to reserve the bytes. So we're going to have byte 0, byte 0, byte 0, byte 0, and byte 0. So assuming in assembly, I'm already giving you this to represent an array of 5 bytes or 5 characters. How do you write the code to do that initialization? What do you think? Okay, so first of all, if I use C syntax, what is this byte designating? ARR bracket 0. Very good. This is ARR bracket 1, 2, 3, 4. Okay, let me write that as comments too. This is the same as that. That's the same as that. Oops. Okay. So So now the question is, knowing this is how we translate in how we allocate memory in C into assembly. How do we get that loop done? Specifically, when we have ARR bracket C equals to something, okay? I don't care what it is, just say X, okay? How do we implement it? How do we figure out the address of ARR bracket C? I mean, C is a register. Go ahead. You cannot do it with register C alone, okay? You need another register. What is the address of ARR bracket C? This is basic C question, okay? So ARR, the address of ARR bracket C is what? What is the other way to express it? It's ARR plus C. Okay, because ARR as a label is the address of byte 0. So ARR bracket 0 is no different from just ARR itself when we are talking about the address. Okay? So when you want to do something like this, how do we do it? So let's say we can use register A, as a scratch register. LDIA with ARR. What does that do? Register A is now doing what? I'm loading register A with the label ARR, and the label ARR is the address of what again? The first byte, or byte 0 of the array. So that means after the LDI instruction, register A points to the first byte of the array. But tag, we don't want the first byte. We want to get to the byte that is indexed by register C. So how do we get to the address of that byte? The byte that is indexed by register C. Aha, very good. So if I were to comment this using C notation, which is always kind of a double-edged sword, okay? This now becomes the address of ARR bracket C. Does that make sense? Okay? Is that good so far? So if we know the address of the byte that we are supposed to update and it is now in register A, how do we store a value into it? Let's assume that whatever value we are supposed to store is in register B already, okay? So assume register B has the right-hand side value, okay, which is X. So assuming that is already in it, what is the next instruction that I need to update that location? There are only two instructions that can use a register as a pointer. One is LD for load, the other one is ST for store. So which one do we use here? Are we loading or are we storing? We are storing. So that means that ST A, comma B is going to get a job done. Is that okay? But hold on a second here. The original code is a little bit more complicated than this because we have to compute 5 minus C. How do we get B to become 5 minus C? Okay, so out of 5 minus C, which one is the subtrahend and which one is the minuend? 5 is the minuend and C is our subtrahend. Okay, so once you identify the minuend and the subtrahend, then we think of the subtraction instruction, SUB, right? So with the SUB instruction, it takes two registers. The first register is that the minuend or the subtrahend? is the minuend. And then the second operand or the second register is our subtrahend. Okay, so register C can be used just as itself, as a subtrahend, as the second register. But 5 is a constant. I cannot put a 5 in SUB because SUB requires a register as the first operand, the first component. So what you need to do is to do LDI B5 so that you put the constant 5 into register B. Then you can do SUB BC, so you subtract C from B. B was 5 to begin with. Now it is 5 minus C. Then your B will fit the criterion that we had in the code, where B is the value that you want to store. Is that okay? So writing assembly code is just that. Okay, you understand the C code, what the C code is doing, and then you try to translate that into the available instructions that we have in assembly with the TTP. So how do you study for something like that? You have to understand the instructions. Okay, so every single instruction, you have to understand what it does. There are categories of those instructions. The LDs and the ST instructions, including LDI, they don't really do much. They only store and load. Okay? And also the CPR, which is another type of load instruction, except it copies from one register to another register, copy register. We have conditional branch instructions, which are useful for loops and conditional statements. We have unconditional branches, JMPI and JMP itself. Those are good for jumping around something, jumping back to the beginning of a loop, that sort of thing. We have calculation type of instructions, add, subtract, and, or, right shift, bitwise not, and I think that's all of those. Okay, so those are all for calculation purposes. And then we have increment and decrement. They're also for calculation, but they do not update the flags. That's the only difference between add versus increment. Increment does not affect the flags. Then we have Cmp Compare, which is particularly useful for conditional statements because we can check whether something is less than something else, or equal to something else, or not equal to something else. So you have to be familiar with all of those instructions, okay, what each one does. Then when you look at the C code that looks like this, then you try to break apart each line into individual operations where each one can be implemented in assembly using instructions. I cannot explain that process any further than just saying that it's kind of like playing with Legos. You look at a Death Star, okay, and you're given a whole big box of Lego pieces. So now the question is, what Lego pieces are you going to use to make a replica of the Death Star? which Death Star, right? I don't know. I just how many Death Stars are there in the entire movie franchise? There are 4 now? I thought only 3.
It's a generic super weapon that's arbitrarily large and you have to blow it up.
But I have a way to draw the 3 Death Stars. The most recent one I think is the biggest one, right? Yeah. And then the 2 are behind it. The 3 Death Stars.
I love if they have a super weapon that's not a giant planet-sized one, but it's just like the size of a box. Like it's small instead of massive.
Yeah, I think they're.
An interesting twist.
I think they're still way underpowered because.
But then they have a super. They do have a planet-sized super weapon, but it's just bait. It's not the actual Death Star. The Death Star is just.
And the Death Star has to draw fuel from the sun to fuel itself. But the TARDIS has a sun inside it as its battery.
Exactly.
So who's going to win, the TARDIS versus the Death Star? I think the result is pretty clear.
I don't think fusion is that hard to do, but you can't.
Well,
Faster than light, I'm pretty sure you can make your own fusion engine.
and if the TARDIS loses the first time, it can always